We shall continue with our study of functional dependencies. We have studied several other integrity constraints like domain constraints, referential integrity constraints, and we just began the concept of functional dependencies. And we found out that if we have a relation scheme R or any set of attributes R, and alpha beta is a subset of this relation scheme or this set of attributes, then alpha to beta is a functional dependency, which means that beta is functionally dependent on alpha. And in any relation R of type R, if there are two tuples T1 and T2 such that the alpha part is same, then the beta part must also be same. This is the meaning of a functional dependency. It puts in the constraint that these attributes are dependent on the values of these attributes. It is not value dependent in that sense, it is equality dependent. That is, it puts in the constraint that two tuples having the same value in the attribute alpha must have the same value in the attribute beta. And we saw several examples. We will quickly recollect one or two of them. This was the flights example, where we had the flight number, the city of arrival, the city of departure, and the plane type as one relation. The number of seats free was the flight number, the date, and the number of seats available. And we found out that flight number to city of arrival, flight number to city of departure, and flight number to plane type are three functional dependencies. And we have another functional dependency stating the flight number and the date is this number of seats available, which means that whenever the flight number is the same, the city of arrival and the city of departure must be same. Indirectly, flight number becomes the primary key or a candidate key for this relation. Here, flight number alone is not the candidate key, but for a flight at a particular date, the number of seats becomes fixed. That is, there can be no two tuples in seats free which have the same flight number and date and have different number of seats available. So, they can't just exist duplicate tuples like that, and non-duplicate tuples which have different number of seats. So, this puts in constraints which help us to define the mapping, the degree of mapping, which is 1, 1, on to many 1. Those are generalized by functional dependencies, and the concept of primary keys is also generalized by functional dependencies. That is, if R is the relation scheme and we have alpha to R, and if we can show that alpha to R holds, then alpha is a super key of R. So, a functional dependency is a constraint which says that beta is dependent on the value of alpha, and if we say that R is dependent on alpha, then this means that alpha is a super key of R. Going back to the book example, we had the book, the user, supplier, borrow, and sup relation, and we had a number of functional dependencies, and we can club them together and write it this way. Actually, what we had was accession number gives year of publication, accession number gives title, accession number gives card number, accession number gives date of issue, accession number gives supplier's name, accession number gives price, and accession number gives date of supply. Instead of writing them independently, we can write them one after another like this as also. Similarly, card number gives both borrower name and borrower address, and supplier's name gives supplier's address. These are the functional dependencies that hold here. So, functional dependencies were useful in expressing candidate keys, expressing primary or candidate keys, or super keys. Additionally, we could also have functional dependencies between attributes which are not primary keys. Primary or candidate keys. For example, suppose we had this functional dependency in the user relationship. Now, bname to baddress does not make bname a super key, because here we have got card number, bname and baddress. Card number implies bname and card number implies baddress. If we add bname to baddress, that does not make bname a super key here, but it just puts in the additional constraint that we cannot have two tuples with the same name and different address. That is, all those persons must have a unique address. Each and every person must have a unique address. Two persons cannot have the same address. So, it is not merely to express candidate keys, but to express other relationships between the attributes. Let us see another example. This was an example which we picked up yesterday, and I made some minor error in expressing this. This says S name, date of supply and price, and we argued that whenever S name and date of supply are same, price must be same. The implication which we tried to convey was that the same supplier on the same date can supply only one book, but that is not true. If there are two books which he has supplied but they have the same price, then that is also allowed. That is, the same supplier can supply on the same date two books with two different, which will have two different accession numbers. Therefore, there will be two different tuples in the SUPP sub relation, but their price will be same. So, this means that the same supplier or a supplier can supply books of a particular price on a day. That is what it means. In a particular day, a supplier can supply any number of books, but they must be of the same price. Of a particular here means same price. It is like, it can be read better this way: a supplier can supply books of the same price on a day. That is the constraint. What is card number and date of issue? If I have this constraint, it means that for the same card number I can have more than one date of issue. That does not mean that in the borrow relation, these two are occurring together in the borrow relation. Therefore, in the borrow relation, which is borrow, accession number, card number and date of issue, in the borrow relation we cannot have two tuples which have the same card number and different date of issue. Now, does that mean that a person can issue only one book on a particular day? That does not mean it. A person can issue as many number of books he wants on a particular, on a person can issue as many number of books he wants, but he must issue all books on only one day. So if I put in this constraint in the database, then it will make sure that any person who has issued books 1, 2 or 4, all of them are issued on the same day only. That is what this constraint means. And whenever I have a functional dependency, during insertion or during updation, this functional dependency will be checked to hold. If this functional dependency does not hold, then the updation or the insertion operation will not be allowed to take place. That is the application of the functional dependency from the point of view of checking of integrity constraints. We will see the application of functional dependencies from other points of view as well. Next, we see the concept of a full functional dependency. Let us see what is the difference between any functional dependency and a full functional dependency. In the book relation, we have accession number to year of publication. We could also have written down, since this one holds, we can also write down accession number now the point is, where does this hold? This one does not hold in any particular relation of the database, but it says that two tuples cannot exist which have the same accession number, same card number and different date of year of publication. Now this does not, all of them does not hold in any particular relation. So moreover, this one which is a subset of it already exists, therefore in any way card number is redundant. And even if it holds in a particular relation and you write down accession number comma title to year of publication, here also title is redundant even though all of them are in the book relation. I can also write down accession number comma title year of publication, sorry, accession number year of publication comma accession number. Even this is redundant. So a full functional dependency is that when it does not contain any redundant attributes. We will have to understand the concept of redundant attributes in two different ways. Firstly, an attribute may be redundant by itself because accession number gives year of publication. Therefore, accession number title year of publication is directly, we can say title is redundant. Now suppose we have this one, accession number gives supplier name, accession number gives supplier address, and supplier name gives supplier address. Now here individually there is no redundancy, but we can see that from supplier name gives supplier, accession number gives supplier name and supplier name gives supplier address will logically should mean their accession number gives supplier's address, because if in any place we have two tuples which have got the same accession number, they must have the same supplier name, and if you have the same supplier name, they must have the same supplier address. Therefore, if this and this is there, then this is redundant. Therefore, accession number, supplier name and supplier address and supplier name with supplier address, in this particular case this one is redundant. So, we had an example before here where on the left hand side something was redundant. Now, we have an example here where something on the right hand side is redundant. Now, to understand how the concept of detection of redundancy, we have to understand how a set of functional dependencies logically implies another functional dependency. That is, how accession number to S name and S name to S address, we have shown that these two together implies accession number to S address. Now, is there any other type of thing that we can derive from this? Is any other functional dependency available? To understand what is the concept of one a set of functional dependencies logically implying another set of functional dependencies, we need to understand what is called the closure of a set of FDs. Redundancy will only be understood when we understand the concept of closure of a set of functional dependencies. A functional dependency is said to be full functional dependency if it has got no redundant attributes. But to understand that itself, we require to understand the logical derivability of attributes. So, the issue that we will take up now is the closure of a set of functional dependencies. We define F plus to be the closure of a set of F, where F is a set of functional dependencies, and F plus is the set of functional dependencies which logically follow from F. Before we take up this example, we take up the example like this. This is from the book relation, this is from the user relation, this is from the, this is not from the user relation, this is from the user relation, this is from the borrow relation, this is from the supplier relation. We have S name to S address, and from the sub relation we have accession number gives S name and price and date of supply. Now, from this we can put in several other things. One of them is accession number gives card number and card number gives borrower's name and borrower's address. So, we can immediately derive accession number gives borrower's name comma borrower's address both, and we can also say that accession number gives supplier's name gives supplier's address. Therefore, accession number gives supplier address as well, and clubbing all the accession numbers together we will get what we had written down first. So, we need not initially define all the functional dependencies, we can define only a set of functional dependencies which are sufficient based on the relations that we have, and the other set of functional dependencies will be derived from this. Among these, for the sake of completeness, we will also have the obvious ones. Accession number gives accession number. Similarly, year of publication gives year of publication. Also, we will have the irredundant ones in the complete database. We will have year of publication comma accession number gives accession number. This is also a valid functional dependency. Year of publication accession number gives accession number, and that way if we start listing out all the functional dependencies, that will give us the closure of the set of functional dependencies, each and every one which are applicable. Now, here many others will be applicable. S name comma S address will imply S address. S name comma price will also imply S address. That is also a functional dependency. S name comma price gives S address. That is another functional dependency which logically follows from this set of functional dependencies. Therefore, closure F plus is the full set of functional dependencies which follow from F. So, if we take this example, we will have to list out all of them. From A to B, we get AB to B, we get AC to B, we get AD to B, and so on, all pairs of 2, then all of 3 containing A, then all of 4 containing A. Here we can have A, B, C, D gives B. So, this way all of them plus the ones derived in a less obvious manner like this, A to B and B to E, so A to E, A to C and CD to E, therefore AD to E. Similarly, AD to F. So, we have the set of functional dependencies which logically follow from F. The next question which we will have to answer at this point of time is, how do we compute the closure? What is the mechanism to compute the closure? Is there an algorithm to compute the closure? In fact, there are many algorithms to compute the closure of a set of functional dependencies, and we have with us a mechanism called Armstrong's mechanism. Armstrong's method to compute the set of functional dependencies, that is to compute the closure of a set of functional dependencies. So, next is it is usually called Armstrong's axioms. What Armstrong did was, Armstrong suggested three rules. Namely, one was called the reflexivity rule, the second was called the augmentation rule, and the third was called the transitivity rule. Each rule suggested how, given a set of functional dependencies, how the rule may be applied to generate one or more new functional dependency which is logically derived from the given set. And he suggested three rules, and he proved that using these three rules only, you can get, by continuous application of these three rules only, you can get the whole F plus. That is, you can compute the closure of the set of functional dependencies. So, we shall first see what these three rules are. These are very simple rules and often widely used to compute the set, understand what is meant by the closure of the set of functional dependencies. The first one is the reflexivity rule. The reflexivity rule gives the obvious, states the obvious. If beta is a subset of alpha, then alpha implies beta. That is, beta is functionally dependent on alpha. Therefore, if beta is a subset of alpha, then alpha to beta holds. So, using this, you can generate a whole set of functional dependencies. The second is, if alpha to beta holds, then gamma alpha to gamma beta holds. That is, you can add one attribute on both sides, the same attribute on both sides, and you can add any number of such attributes, and this also holds. The third is the transitive rule, which we have been using so long. If alpha to beta holds and beta to gamma holds, then alpha to gamma holds. That is, if there is alpha to beta, which means the two tuples having the same alpha must have the same values in the attribute beta, and if they have the same values in the attribute beta, they must have the same values in the attribute gamma, which directly means that if they have the same values in the attribute alpha, they must have the same values in the attribute gamma. The proof that these three rules are correct is quite obvious and can be proved logically very easily. The beauty of Armstrong's axioms was, Armstrong stated that you given a set of functional dependency, you see if this rule is applicable, apply it. If not, see if this rule is applicable, apply it. If not, see if this rule is applicable, apply it. And whatever you get, again you go back and start applying this rule. And you go on applying these three rules. It does not matter, the order does not matter. You go on applying these three rules till you reach a situation where none of the rules, when applied, leads to any new functional dependency. It is at that point the closure has been obtained. The closure will be obtained in the condition that suppose I am given a set of functional dependencies, and by applying these rules on that set of functional dependencies, I cannot generate any new functional dependency, then it is said that the closure has been obtained. Therefore, along with these very three simple rules, Armstrong proved the following result. Armstrong proved that these three axioms are sound and complete. Sound, what does Armstrong's axioms are sound mean? It means any new FD derived by the axioms is indeed a member of the closure. That is, if I use these axioms to derive a new axiom, a new functional dependency, then this new functional dependency must be a member of the closure. That is quite obvious from the three rules which we have studied. The more important proof was that all elements of the closure can be determined by repeated application of the actions. Therefore, the Armstrong's axioms are the necessary and sufficient conditions to obtain the closure of a set of functional dependencies. But Armstrong's axioms are not, while these axioms are necessary and sufficient, we may see that there are additional axioms which are useful in deriving newer functional dependencies. Like we saw in the original relational algebra, we saw the fundamental operations and we saw additional operations, and we found that additional operations like natural join, which though they may be written down in terms of fundamental operations, the natural join operations are more useful and more widely applicable in solving problems. Similarly, while Armstrong's axioms are, these are the three fundamental axioms, there are other rules which are also useful and can be used to generate the newer functional dependencies. We will discuss three such important rules. The first rule is the union rule. It says that if alpha to beta holds and alpha to gamma holds, then alpha to beta, this is alpha to beta holds and alpha to tau holds, then alpha to beta tau holds. We assume that this was obvious. Now we have got a syntactic rule to prove it. The second is the decomposition rule. If alpha to beta gamma holds, then alpha to beta holds and alpha to gamma holds. And the third is the pseudo transitivity rule, which says that if alpha to beta holds and gamma beta to delta holds, then gamma alpha to delta holds. So there are three rules. union, decomposition and pseudo transitivity, which can be used to derive some newer functional dependencies, possibly faster than using the standard 3 axioms of Armstrong. But these 3 rules are not independent in the sense that they can be derived using Armstrong's axioms themselves. For example, let us see the union rule. The union rule says if alpha to beta holds and alpha to tau holds, then alpha to beta tau holds. We assume this is obvious from our AND OR logic. If alpha to beta holds, then alpha to tau holds, then alpha to beta and tau holds. But now we are looking at it from a pure syntactic point of view in terms of an algorithm which will derive, reading this and this will derive this based on Armstrong's axioms. Now let us see how that is true. From Armstrong's axioms we have this holds. Using the augmentation rule, we have alpha alpha to beta alpha. Now alpha alpha, this is a set. So alpha alpha is the same as alpha. Alpha alpha is the same as alpha. So this means that alpha to beta alpha holds. So this is one side. On the other side we have got alpha to tau, and using the augmentation rule we have beta alpha to beta tau, and based on this and this and using the transitivity rule we will easily derive that alpha to beta tau holds. So the union rule can be derived from Armstrong's axioms, but it is a useful rule when we apply it directly. Similarly, decomposition rule can also be derived from Armstrong's axioms. The decomposition rule says if alpha to beta gamma holds, then alpha to beta and alpha to gamma holds. This can also be derived easily using Armstrong's axioms. We have got alpha to beta gamma and we have got the reflexivity rule which says beta to beta. Okay. So can you derive from using this and this? Can you derive this? See, this is this rule, and this is reflexivity rule. But using these two, we are to now derive. Our goal is to derive this and this. So we will derive them. We can derive them separately. We can derive this one from this and this one from this. We have to derive these two separately. So alpha gamma gives beta gamma, and beta gamma is, we will have to use the union rule to derive this. Anyway, we will have to prove this first. If we can prove this and we have this, then we will use the transitivity rule to derive this. but this one has to be first proved using Armstrong's axioms. Armstrong's axioms are only 3 rules: alpha to beta, gamma alpha to gamma beta, and this is the transitivity rule. So, we do not have any direct rule proving this. We have to first prove this using some rule and then use this to prove this. I will not complete it, I will just leave it as an exercise to show how given this you can prove this. Similarly, how given this you can prove this. And also using the pseudo transitivity axioms, the pseudo transitivity rule, alpha to beta holds and gamma beta to delta holds, then gamma alpha to delta holds. This can also be proved very easily using the Armstrong's axioms, because you put gamma this side and gamma this side, you will get gamma alpha to gamma beta, and you have already got gamma beta to delta, so you will get gamma alpha to delta. So, like the additional relational algebra operators, you have some additional rules. So, using these rules we can find what is called the closure of a set of functional dependencies. Another useful item, so we have got the concept of F, which is the set of functional dependencies. We have got the concept of F plus, which is the closure of the set of functional dependencies. Now, the closure can also be found in another manner. The closure can be found by what is called the closure of a set of attributes. If alpha is a set of attributes of a set of functional dependencies F, then alpha plus F, or sometimes it is denoted by alpha plus F, is that set of is the set of attributes which are logically determined by alpha. Let us go back to our original example to understand this. We had accession number to card number, and we had date of issue. We also had accession number. Let us pick up the example, I think I have it somewhere. We had accession number to year of publication and title. We also had accession number to S name, price and date of supply. We had card number to borrower's name and borrower's address, and we had card number, we had S name to S address. Now, based on these, we would like to find out all the attributes which are dependent on accession number. The attributes which are dependent on accession number on this set of functional dependencies F is called the closure of this attribute under F. Here we will have this one, this one, this one, this one, this and this, because they are directly implied. We will in addition we will have borrower's address, borrower's name as well as supplier's address, because all these attributes are indirectly also determined or dependent on accession number. Therefore, the accession number will have card number, date of issue, year of publication, title, supplier's name, supplier's address, price, date of supply, borrower's name and borrower's address in the closure of this attribute accession number. Now, this need not be a single attribute, it may be a set of attributes. Formally, closure of an attribute set alpha is said to be alpha plus over F. It is always over a set of functional dependencies, and it says it is the set of all attributes functionally determined by alpha under a set of F of functional dependencies. Let us take another quick example here to understand the meaning. What is A plus here? This is the set of functional dependencies. A plus is equal to A obviously, B, C. Now B, A implies B and AC gives D. A implies C and AC gives D. Therefore, A will give D. So, A plus is A, B, C, D. B plus D gives B, but B gives nothing. Only when combined with A it gives something. So, B plus is B. Similarly, you can compute C plus, you can compute D plus. Then you can compute what is AB plus, you can compute AC plus, you can compute AD plus, then BC, BD, all pairs of 2, all pairs of 3, all pairs of 4, and this way you can get the closure F plus also. Using this, using the closure of the set of attributes, you can also get the closure F plus. There is a very simple algorithm to compute the closure of a set of attributes, and I just mentioned this attribute algorithm here. We have got alpha. A set of attributes alpha is given to us and a set of functional dependencies is given to us, and we will compute the closure of alpha. Before just presenting the algorithm, I will mention what this algorithm, how this algorithm works. It starts with alpha, it picks up functional dependencies one by one, and if a functional dependency is of the type X to Y and there is alpha is initially stored in a temporary set R, and if X is a subset of R, then R is assigned R union Y. You initialize R to alpha and you pick up a functional dependency. If that functional dependency has X, which is a subset of R, then obviously you can say that in the closure of that set of attributes, Y must also be there. So you put Y there, and you go on doing this till for no functional dependency you can make any more additions to this set. and the simple algorithm is this. Initialized R, which I have written as result to alpha, modified is true, modified indicates whether there has been any change. While modified, that is while modified is true, you make modified false, and then for each functional dependency in a for loop of the form A to B, where this is a set of attributes, this is another set of attributes, you do this. If A is a subset of the current result set of attributes, then you add B to that and say that some modification has taken place, and you do it for all the functional dependencies. Now, if there is any one functional dependency for which an addition has taken place, this outer loop is executed again, because modified becomes true. The program exits when, after entering this phase, for no, this one does not hold. That is, for no functional dependency, this is true, and this modified really takes place. There is a slight mistake here. The mistake is that even if A is there, it will still have this. So we must make result union B, modified is true if result changes. That is, if the value of the attribute set changes. Because suppose if this statement was not there, then what would have been the case? Suppose I had A and I had a functional dependency A to B. So in A plus, I would have put A, then I would have put B, and then this would still hold A to B, and result would add B, and nothing would happen under union. That is, result would not change, but still modified would be true, and the program would go into a loop. So to prevent that loop, we must make sure that this modified is made true only if actually something new is entered into this set. So this is a simple algorithm to compute the closure of a set of attributes. Using these ideas, we come back to our original concept of irredundancy. So to understand irredundancy, we have to understand what is meant by the cover of a set of functional dependencies. Let F and G be two sets of functional dependencies on a relation scheme R. That is, we have got R and we have got two sets of functional dependencies, F and G. We say F is a cover of G if F plus is equal to G plus. That is, they are equivalent. You can also say that F is equivalent to G. So F is a cover of G if F is equivalent to G. That is, the set of functional dependencies which are logically implied by F are the same as the set of functional dependencies which are logically implied by G. The use of cover is important because that leads us to the concept of a minimal cover. Now we can have many covers of a set of functional dependencies. A cover is said to be minimal or canonical if it has no redundant term. That is, now we want to find out a smaller set of functional dependencies so that all that which we wanted to imply we will have. Our idea is, if we have borrower's name to borrower's address, accession number to borrower's name, then this is sufficient, and we will not want to write down additionally accession number to borrower's address, because this functional dependency f covers this G, because f plus is equal to G plus, and we would like to have the smallest set here, so that is sufficient to express ourselves. We do not want to express more than one unnecessary redundant attribute. To do that, we have to remove, as I had mentioned earlier, those which are on the left and those which are on the right. I will take a quick example before terminating. Let us see A to BC, AC to D, D to B, and AB to D. Now let us look at this. A goes to B and A goes to C. AC goes to D. Therefore, we can simplify this and say A goes to D, because A goes to C itself, and if AC goes to D, then A goes to D. Similarly, we can remove this and write A goes to B, and A goes to B is here, A goes to B is also here. So this one is useless. So this is out, and we are left with only two, A goes to BC, D, and D goes to B. Remember, D goes to B cannot be removed. Even if A to D is there, D goes to B does not get removed, because D goes to B is separate. Therefore, we will remove these, the redundant attributes on the left as well as on the right, and we will write it out this way. We can now also remove B, because A goes to D, D goes to B, therefore B is removed. So after removing the right hand side, we can now remove the left hand sides and say this is our canonical form, or this is the minimal set of attributes. And the minimal set of attributes is useful because that is sufficient to express all our information regarding functional dependencies. We will see the use of functional dependencies in a different form in the next class.